Welcome back. So, let us continue. Now, we move on to the case of 3 risky securities. Now, this is the real representation of the general case or the n securities case. The 2 security case had certain singularities because we could develop the entire theory on a 2-dimensional representation. However, in this case the situation gets more intriguing, more interesting, and it is here that we encounter the aesthetic beauty of this particular theory. So, let us get into it quickly. So, an analysis of the 3 securities elucidates some intriguing features of the portfolio optimization problem. I shall illustrate this by virtue of an example, because otherwise what will happen is the calculations and the expressions would be so cumbersome that the real nuances would be lost in the plethora of calculations. So, I will take this up in the form of an example and illustrate each and every step which goes into this theory for 3 securities or more than 3 securities. Let us start with the 3 securities. So, let us consider 3 securities A, B and C. The standard deviations and the expected returns of the 3 securities are given on the slide. 6%, 3%, 15% are the standard deviations and the expected returns are 14%, 8%, 20% for the 3 securities respectively. We are also given the correlation coefficients between the various pairs of securities. Rho AB is equal to 0.5, rho BC is equal to 0.4 and rho CA is equal to 0.2. Now, what are the feasibility defining equations? These are standard. I believe the learner would have become familiar by now. We have the expression for sigma p of the portfolio, which is given here on the right hand side, the first equation on the right hand panel, then the expression for the expected return on the portfolio, which is the second equation, and then we have the aggregate of the weights must be equal to 1. I am representing sigma p by x, r p bar, that is the expected return, by y, and x 3 by 1 minus x 1 minus x 2 as z. Now, the important thing is, please note here we have got 5 variables x I, that is the composition vector which has 3 components, x 1, x 2, x 3, plus we have sigma p and we have the expected return of the portfolio R p, but we have only 3 equations which are shown on the panel of the right hand side, and therefore, we can eliminate 2 unknowns, but we are left with 3 degrees of freedom. And to represent these 3 degrees of freedom, I choose the 3 coordinate axis or 3-dimensional space with x representing the standard deviation, y represented the expected return of the portfolio, and z represent the composition of the third security, security C, which we have. So, z is representing x 3. Now, when we simplify the expressions, when we eliminate x 1 and x 2 and within this panel of equations, within this set of equations, if we eliminate x 1 and x 2, we get an expression between or a quadratic between x, y and z, which is given in this particular slide. X square minus 3 by 4 y square minus 3006 z square plus 12 y minus 162 z plus 18 y z minus 57 is equal to 0. Now, let me repeat, this is obtained by eliminating x 1 and x 2 between the 3 equations that were given in the previous slide. If you eliminate x 1 and x 2, substitute sigma p equal to x, r p equal to y and x 3 equal to z, what we get is this expression which is represented by equation number 40. Now, if you look carefully at the shape of this particular equation or the representation of this particular equation in the 3-dimensional space, what we find is that irrespective of the value of z, what we find is that the quadratic or the second degree equation represents a hyperbola. In other words, whatever value of z you take, you end up with a hyperbola. So, what does this mean? This means that given this equation in 3-dimensional space, if I pick out any value of z, say z equal to 1 by 2, then I get a hyperbola by plotting different values of x and y on the plane which has the equation z equal to 1 by 2. In other words, the plane which is parallel to the xy plane and which has a z intercept of 1 by 2. So, for every value of z, now if short sails are allowed, then the value of z can range from minus infinity to plus infinity. So, for every value of z, let me repeat, this is fundamental, this is very important. For every value of z along the z axis, if you pick up any value of z, you get a hyperbola with the points on the hyperbola being confined to the plane that is represented by z equal to the given values, let us call it alpha. So, if you pick up any value of z equal to alpha, then the plotting of x and y with z equal to alpha, you pick up z equal to alpha, you fix z equal to alpha and you plot x and y, what you get is a section of the hyperbola just like in the two securities case, but the section of the hyperbola will lie on the plane that is given by z equal to alpha, or a plane which is parallel to the xy plane, but at a distance of alpha from it. So, that is the shape of this second degree equation. It comprises of a family of hyperbola, which can be identified with the value of z, because that hyperbola will lie on the plane which is represented by z equal to alpha, parallel to the xy axis at a distance equal to alpha from the xy plane. I am sorry, not xy axis, xy plane. So, this will show you, I have done my best to present this situation which I just explained in the form of a diagram. We have the z axis or the x3 coming out from the plane of this particular tablet, and we have the expected return upwards and the standard deviation towards the right. So, this is the 3-dimensional framework. If you pick up any point on the z axis and you have a plane which is parallel to the xy plane cutting the z axis at that point, which is say let us call it z equal to alpha, then if you plot x and y with z equal to alpha being fixed, you get a hyperbola, for example, which is shown here in this diagram as containing the point p dash. So, this is how the portfolio possibilities region would look like. If now what we are, please note, we are examining the case where where short sales in all the 3 securities are allowed and riskless borrowing and lending is allowed. So, what we do now is we draw tangents from the point 0 r f comma z equal to alpha. Let us say we identify this plane by z equal to alpha. So, this particular point, let me illustrate it. This point here has the coordinates. What are the coordinates of this point? Let me call it r f. Suppose I pick up this point r f, which is lying on the plane z equal to alpha. What will be the coordinates of this point r f? The coordinates of this point r f will be, x coordinate would be 0, because this is representing 0 as sigma p is equal to 0. This is the 0 risk point. The y coordinate will be equal to the risk free rate, and the z coordinate will be equal to alpha, because it is lying on the plane z equal to alpha parallel to the xy plane. So, the coordinates of this point will be 0 comma r f comma alpha. What we do is, from this point 0 comma r f comma alpha, we draw a tangent to the hyperbola that is lying on this plane z equal to alpha. By plotting various combinations of x and y, we get the hyperbola, let us say r f p dash. I am sorry, we get the tangent, not the hyperbola, we get the tangent r f p dash, which is tangent to the hyperbola that lies on the plane z equal to alpha, and which is obtained, the hyperbola is obtained by plotting various combinations of x and y with z equal to alpha being fixed. Similarly, for each value of alpha, we will have a similar situation for alpha equal to say alpha 1, alpha 2, alpha 3, whatever the. So basically the portfolio possibilities region would be a combination or a family, rather family of hyperbola, and together with these kind of tangents, depending on what we choose for the position or the scenario that we choose, insofar as short selling of ABC is allowed or not, and whether risk free borrowing is allowed or not. This would be the hyperbolas and this would be the tangent. So then you can apply the theory that we have discussed earlier for the two securities case. So this is how it would evolve, this is how the situation would evolve. Now our problem is to obtain the optimization or the efficient frontier. How to obtain the efficient frontier? Let us look at the case where we have short sales in all the most general case, short sales in all the securities is allowed and risk free lending and borrowing is allowed. Then what did we do in the previous case? When we discussed the two securities case, we tried to maximize the slope of this particular line RFP dash, which would give us the tangent. Now in this case what we would do is, corresponding to each z equal to alpha, we would try to maximize this particular this slope RFP dash. For every value of alpha, we have this kind of hyperbola, we have this kind of situation, and in every value of hyperbola, we try to maximize the slope, and we will get different points like p dash on each of the hyperbola corresponding to each value of alpha. We out of this family of hyperbolas and these tangents to each of these hyperbolas, we pick that particular hyperbola, we pick out that particular hyperbola, listen carefully, for which the slope is the maximum. So the first step is that we try to find out the slopes of all these hyperbola which lie on different planes parallel to the xy plane at different points along the z axis. For each of these planes, we will get a particular tangent which has the maximum slope, because the tangent is obtained by maximizing the slope. So and then we out of this maximum slopes, we pick out that slope which has the maximum value. That gives us the optimal hyperbola. That gives us the optimal hyperbola, the hyperbola that we now need to focus on, and the corresponding, of course, corresponding intercept or the plane on which that optimal hyperbola lies will be represented. Obviously, again it would be a plane parallel to the x axis, and that would be represented by, let us say, some value of z, let us say z equal to alpha. Then z equal to alpha plane, which has now been selected as the plane which contains the hyperbola for which the tangent has the maximum slope, that is our optimal hyperbola. And then the next step is, so this is the first step of the optimization process, maximize the slope of the hyperbola. The second step is and then pick out the hyperbola with the maximum of those maximized slopes. The second step is that we now try to work out the coordinates of the point of contact of this particular this special hyperbola which corresponds to the maximum slope with the tangent. In other words, that point p dash which you are representing in this diagram, we try to work out the coordinates of this p dash, where this p dash is the hyperbola which is the optimal hyperbola, which is the hyperbola having the highest slope of the tangent. So this point p dash coordinates we can work out just as in the case of two security problem. X and y coordinates can be worked out, and the z coordinate will obviously be z equal to alpha, because this entire hyperbola as well as the tangent there too will lie on the plane which z equal to alpha, which is parallel to the xy axis. So let me recap all these steps and then we will move forward. So the portfolio optimization problem in essence boils down to number 1, identifying that hyperbola out of the family of hyperbolas represented by Hz, where z is the point on the z axis, an arbitrary point on the z axis, which is such that the value of tan theta r p minus r f upon sigma p is that is the slope of the tangent drawn from f comma r f comma z to the hyperbola is maximum. So, for each of these hyperbolas we try to draw the tangent, and then out of those entire set of hyperbolas with their tangents, respective tangents from these points 0, r f and z, we find out that hyperbola for which the slope is the maximum, that is the special hyperbola which is the optimal hyperbola. Let this hyperbola be h alpha, which has the maximum slope. Okay. So, once this hyperbola is identified, to obtain the coordinates of the point of contact of the tangent that has the maximum slope with the hyperbola h alpha to which it is tangent, that is the next step. First of all, we identify that hyperbola h alpha which is such that the slope from the point 0 r f comma z, or in this case it would be z equal to alpha, to the hyperbola is the maximum of all those hyperbolas and all those tangents to those hyperbolas. Then we find the point of contact of this tangent with this optimal hyperbola. Now, the efficient frontier in this case, where short sales and all the securities is allowed and the risk free lending and borrowing are allowed, simply the tangent line joining the point f 0 r f alpha and the point of contact we extended indefinitely. This is the point that we are talking about is the point of contact of the tangent with this optimal hyperbola. So, that is the situation, that is the geometry of this particular 3 security case. It becomes very intriguing, very interesting. Now, we do the maths. Obviously, the first step is to find the hyperbola with the maximum slope for which, or the tangent with the maximum slope for which we maximize the function tan theta is equal to r p minus r f upon sigma p. We substitute r p as sigma xi ri, and then we use the fact that sigma xi is equal to 1. So, that we can write the numerator in the form that is given in equation 41, the denominator is written in the usual way. Now, for optimality, as you can see, we maximize theta. We have discussed this in a lot of detail earlier. This is called the Sharpe ratio. And when we do the maximization exercise, we differentiate with respect to each of this. What are the free variables? The free variables are the composition vector or the components of the composition vector, capital X1, capital X2, capital X3 and so on. If it's an n security portfolio up to capital Xn. In our case, we are having a 3 security portfolio. So, our independent or the free variables are X1, X2 and X3. So, we differentiate this expression for tan theta or the Sharpe ratio with respect to x1, x2 and x3 partially, and then we do some algebraic simplifications, and after doing this algebraic simplifications we get this set of equations which is represented right at the bottom of your slide, which is called the fundamental form of the optimization equations. So, this is equation number 42, which is the fundamental form. Now, please note these are a set of n equations. We have n unknowns x z1, z2, z3 and so on up to zn. So, they should be sufficient to give us a unique set of z's, z1, z2, z3, and from which we can extract out the x1, x2, x3 by using this expression right at the right hand corner of your slide. Knowing all the z's, we can work out the x's as well straight away. So, we have these n equations in z's and we have n unknowns. So, we can get a unique set of z's, and from there we can obtain the complete set of the components of the composition vector. So, thus we get a set of n equations for an equal number of unknowns being the components of the composition vector, which would in the normal course have a unique solution corresponding to the point of contact of the tangent to the hyperbola H alpha identified as above. Knowing the composition vector, we can calculate the corresponding coordinates and risk return space of that point of contact, and let us call that point P dash, and then we can, because we know the coordinates of P dash, we know the coordinates of the risk free point, that is 0, R f and alpha, and therefore, we can find out the equation of the straight line joining the point R f and P, which represents the efficient frontier. So, now let us continue with this problem. So, we now continue with the 3 security problem, and we assume the risk free rate at 5%. We are making this assumption that the risk free rate is 5%. Then we get, if we use the equations number 42, which are given here on the right hand panel of your slide, we substitute the expressions for sigma 1, sigma 2, sigma 3, R 1, R 2 and R 3, and rho 1 2, rho 2 3 and rho 3 1. What we end up is the equations that are given on the left hand panel of your slide. 9 is equal to 36 z 1 plus 9 z 2 plus 18 z 3, 3 is equal to 9 z 1 plus 9 z 2 plus 18 z 3, and 15 is equal to 18 z 1 plus 18 z 2 plus 225 z 3. If you solve these equations, these are 3 equations and 3 unknowns. So, the solution is quite straightforward, and it can be done by any method that applies to simultaneous linear equations. We get z 1 is equal to 14 upon 63, z 2 is equal to 1 upon 63, and z 3 is equal to 3 upon 63. The corresponding values of x 1, x 2 and x 3 are 14 by 18, 1 by 18 and 1 by 6. And the standard deviation, now we have got x 1, x 2 and x 3, we know sigma 1, sigma 2 and sigma 3, we know rho 1 2, rho 2 3 and rho 3 1. So, we have got all the inputs that are required for calculating the standard deviation of the portfolio comprising of these securities in these proportions, and we find that the standard deviation is equal to under root 203 upon 6, and similarly we can work out the expected return on this portfolio, and we find that expected return is equal to 44 upon 3. And so, these are the, now hence what are the coordinates? Now, let us continue with that. What are the coordinates of P dash? The coordinates of P dash are sigma x is equal to under root 203 upon 6, y is equal to 44 by 3, and what is z? Z is the composition of x 3 or the content of x 3, which we have already found, it is 1 by 6. So, the coordinates of the point P dash are under root 203 by 6, 44 by 3 and 1 by 6. So, the efficient frontier is the straight line joining the 2 points R f and P dash. What are the coordinates of R f? Let me repeat, 0, comma, it was the 5, yes, 5% was the risk free rate, and z 3, I am sorry, x 3, which is equal to 1 by 6. So, the coordinates of R f are 0, 5 and 1 by 6, and the coordinates of P dash are, we have already worked it out, under root 203 upon 6, comma 44 by 3, comma 1 by 6. Please note, both these points are coplanar. Both these points lie on the plane z is equal to 1 by 6, which is parallel to the xy plane and at a distance of 1 by 6 along the z axis. And what is the equation of the straight line joining R f and P dash? That is given by x minus 0 divided by under root 203 upon 6 minus 0 is equal to y minus 5 divided by 44 by 3 minus 5, and z is equal to 1 by 6, because the line lies on the plane, z is equal to 1 by 6. So, this is the equation of the efficient frontier, and any point on this line would be an efficient portfolio. It would comprise of the risk free asset, lending or borrowing, on depending on whether the point lies beyond P dash or within F P dash. If it lies within F P dash, then both F and P dash are long, and if it lies beyond P dash, then F is short, that means risk-free borrowing plus P dash, which is long. Now, the final question is, what happens when neither risk-free borrowing nor lending is permitted? Only short sales of risk-free assets is allowed. You see, so far I have tackled the case where short sales in in all the three securities A, B and C was allowed, and risk-free lending and borrowing is allowed. Not but to be able to calculate the entire efficient frontier, we need also to address the situation where risk-free lending and borrowing is not allowed. So, that is the case that we take up now. I will illustrate the procedure. It is again somewhat intriguing, but I will illustrate this procedure in detail step by step. Step 1, we take a risk-free rate for, just like we have already done, we have taken risk-free rate as 5% and we solve the optimization equations. Now, for the given say 3 security problem A, B and C with risk-free rate equal to 5%, we arrived at the composition of the point P dash as, or let us call it point P now. Let us simplify the notation, let us use brevity, let us call this point P. So, this point P where the efficient frontier is let us call RF by the point F. So, the FP is my efficient frontier and the composition of the point P is given, we have already worked it out, it is 14 by 18, 1 by 18 and 1 by 6. This is the composition of the point P, and the coordinates of the point P are under root 203 by 6, 44 by 3 and 1 by 6, and the coordinates of F are 0, 5, 1 by 6. So, this is the situation which we have, all these figures we have already worked it out or are available in the problem. So, the standard deviation and the expected returns are under root 203 by 6 and 44 by 3, and the coordinates of the point of contact I have already mentioned. Coordinates of P are under root 203 by 6, 44 by 3 and 1 by 6. So, this is a point on the hyperbola that lies on the plane z is equal to 1 by 6 parallel to the xy plane. Step 2. Step 2 is you take a second risk-free rate, take a different risk-free rate. Let us say we take a risk-free rate of 2% and again solve the optimization problem. The procedure is exactly same as what we had done earlier. We simply have to substitute RF as 2% instead of 5%. Sigma 1, sigma 2, sigma 3, R1, R2, R3 and rho 1, 2, rho 2, 3, rho 3, 1 would all remain the same. The only change that would occur is that RF would change from 5% to 2%, and when we solve this set of equations, let us call this new point Q. We solve this set of equations, we arrive at the composition of Q as xq1 is equal to 7 by 20, xq2 that is the composition of security A in portfolio Q is 7 by 20, composition of security B in portfolio Q is 12 by 20 and composition of security C in portfolio Q is 1 by 20. The standard deviation and the expected returns can again be worked out in the same way. We know x1, x2, x3, we know sigma 1, sigma 2, sigma 3, we know rho 1, 2, rho 2, 3 and rho 3, 1. So, we can calculate sigma q that works out to under root 5481 upon 400, and we can also work out the expected return because we know R1, R2, R3, we know x1, x2, x3. So, RQ works out to 107 divided by 10. So, the coordinates of Q, that is the coordinates of the point of contact of this new tangent, new hyperbola, new tangent. This is different from the hyperbola that we had for RF equal to 5, that was lying on the plane z equal to 1 by 6. This is lying on the plane z equal to 1 by 20. So, they are not coplanar, please note this. The hyperbola corresponding to RF equal to RF equal to 5% was lying on the plane z equal to 1 by 6. The hyperbola corresponding to z equal to RF equal to 2% is lying on the hyperbola z equal to 1 by 20. So, they are lying on different planes, but obviously both the planes are parallel to the xy plane, albeit at different perpendicular distances from them. So, the coordinates of this point of contact Q, which is similar to the point P in the case of the earlier hyperbola, which corresponded to RF equal to 5%. We now have the point Q, which is the coordinates 5481 upon 400 square root, comma 107 by 10, comma 1 by 20. So, let me reiterate this point. This hyperbola corresponding to RF equal to 2% lies on a different plane from the hyperbola corresponding to RF equal to 5%. That is, the two hyperbola are non-coplanar. Therefore, and in fact, the hyperbola corresponding to different risk-free rates will lie on different planes, but each plane would be parallel to the xy plane and would be at different perpendicular distances from the xy plane. Now, we need to prove a simple theorem. This theorem is that linear combinations of two efficient portfolios is efficient. The linear combination of two efficient portfolios is efficient. The proof is rather straightforward. I will not spend time on it. You simply write out the optimization equations for the two given portfolios. Let us say we have got the portfolio P and the portfolio Q, which we have, for example, which we have just calculated. Let us use these two portfolios. Both are efficient because we were arrived at those portfolios by solving the optimization equations. So, they are optimal portfolios. We use these two portfolios as for illustration, and we write the optimization equations and then we form a combination, a linear combination of the two portfolios in the ratio alpha is to beta, where alpha plus beta is equal to 1. And when we simplify this, we find that the new portfolio that is constructed, that is a portfolio comprising of P and Q in the ratio of alpha is to beta, also satisfies the optimization equations, but with a different risk-free rate. So, this is shown in this particular slide. You can see here that the combined portfolio, the portfolio comprising of P and Q in a arbitrary ratio alpha is to beta, where alpha plus beta is equal to 1, results in a portfolio which satisfies the optimization equations given by or with respect to a new risk-free rate and a new lambda, which are both shown in this particular slide right at the bottom. So, we have established that a linear combination of two efficient portfolios is also efficient. Let me repeat, a linear combination of two efficient portfolios is also efficient. Therefore, it follows that every point on the efficient frontier is a linear combination of two other points on the frontier orbit corresponding to different risk-free rates. Hence, if we know the coordinates of any two points on the efficient frontier, which will represent two efficient portfolios, we can trace the entire efficient frontier, because every other point will be a linear combination of these 2 points. Thus, now if you look at the beauty of this problem, here is, according to me or as per my perception, the most interesting step in this whole analysis. What we find is that a linear combination of two efficient portfolios is efficient. Therefore, every portfolio, every efficient portfolio can be formed, can be expressed as a linear combination of these two efficient portfolios. And that means what? That means we simply need to construct the portfolio possibilities curve or the efficient frontier of this portfolios P and Q, and that will give us the entire efficient frontier that we are looking for. The bottom line is, what I am trying to say is that the entire problem has now been condensed to a 2 security problem. From the n security problem, we have been able to resolve this into a 2 security problem, the theory of which we already know with a lot of detail, which we have already discussed. So, let me repeat, we have established that the linear combination of 2 efficient portfolios is efficient. That means what? That means any portfolio that would be efficient can be expressed as a linear combination of 2 efficient portfolios, and that being the case, now any portfolio means an arbitrary term. That means we are talking about the efficient frontier in totality, because that any portfolio can be any arbitrary portfolio on the efficient frontier. So, in other words, we are talking about the entire efficient frontier, and the entire efficient frontier would be represented by a linear combination of P and Q. But we know how to work out the the efficient frontier of a too risky portfolio problem or too risky security problem. That is the hyperbola arc that we have discussed in a lot of detail. So, the bottom line is, if we know the cardinals of P, the cardinals of Q, what are the cardinals of P and Q that we need to know? We need to know the standard deviation of P, we need to know the standard deviation of Q, we need to know the covariance between P and Q, or the correlation coefficient between P and Q, and we need to know the expected returns of P and Q. If we know all these 5 figures, then we can work out the efficient frontier comprising of P and Q, which would be the efficient frontier corresponding to all portfolios which we are looking for. So, from here I will take up in the next lecture. Thank you.